Welcome to the first part of the statics course. Thank you so much for enrolling. In this two-part course series, you will learn one of the most basic concepts that you absolutely need to know and understand if you want to pursue a career in mechanical, aerospace, marine, or civil engineering. Whenever you design cars, bridges, buildings, cranes, airplanes, helicopters, ships, you name it, you have to make sure that they are all capable of withstanding the required loads. You don't want an airplane's wing to break off during the flight or a bridge to collapse because there was a component somewhere that was too weak and could not withstand the loads that it was supposed to withstand. And so statics will equip you with necessary tools that you need in order to analyze these kind of structures and make sure that you design them for the right loads. This course series has two parts, Statics Part 1 and Statics Part 2. These are the topics covered in Statics Part 1. We'll first cover general principles for statics and dynamics. Here we'll talk about the necessary assumptions we need to make in our statics problems. We'll get the first intuition on forces and moments. We will also talk about the International System of Units, or SI units, and you'll get comfortable working with them. I'll show you an easy way to do unit conversions. Then we'll have a section about vector applications and operations in 2D and 3D. We will learn how to work with vectors and how to apply them to real-life situations in 2 and 3 dimensions. For example, imagine that you have a tower, and so we will use force vectors in order to stabilize that tower with cables. Then we'll have a section about force equilibrium of a particle in 2D and 3D. We will apply force vectors to solve particle equilibrium problems. We will go through many situations where you have to calculate the necessary forces to achieve stable equilibrium for all kinds of cable structures. Then we'll continue with moments in 2D and 3D, where you will get plenty of intuition and application working with them. No longer we'll have particle problems. We will be working with rigid bodies where size does matter. And so, next to forces that make bodies accelerate, we must now know how to calculate moments that make bodies rotate. It's necessary because if you want to keep structures stable, you have to counter their tendency to rotate with a counter moment. Then we'll continue with the section called Distributed Loads in 2D and 3D. Oftentimes, your structures are not subject to point forces only, but rather to distributed pressure forces. We will learn how to describe distributed loads and how to convert them to equivalent point force systems to make our structural analysis easier. Then, I will teach you the difference between the concepts of a centroid, center of mass, and center of gravity for a body. You will see when these three concepts are the same and when they are different when we go through a simple space elevator example. Finally, we will finish this course with a section called Hydrostatic Fluid Pressure and Centroid of an Area, where we analyze underwater structures such as dams, underwater tunnels, water draining mechanisms, and water tanks when they are subject to distributed pressure from water. We will also learn how to find area centroids for complicated shapes. So these will be the topics in this course, but the story will not be over. In Statics Part 2, we will build on that knowledge. We will cover topics such as rigid body equilibrium in 2D and 3D, frames and machines, then virtual work, friction forces, trusses, and internal loads. And by the way, I've also tried making this course more intuitive by using some Python animations to visualize some of the concepts. Python animation tools are a topic on its own, and it's covered in this course. Python engineering animations bring math and data to life. That course will teach you everything you need to know about Python animation tools. And finally, what I want to say is that this course is heavily focused on problem solving. I will be giving you a lot of problems to solve. I will be asking you to pause the video or simply solve the problem before watching the next video, and then I will show you how to solve them myself. It's very important that you are very proactive in this course. Always try solving problems yourself first before watching my solutions. That way you will actually learn and train your problem-solving muscle. It's also very important that you follow this course from the beginning till the end without skipping any steps, because newer topics rely on older topics. And of course, if you find that the lectures go a bit too slow for you, then I recommend watching them at 1.25 speed. So that's the plan for this course. Let's get started in the next video. Thank you very much. Welcome back. So let's talk about some of the fundamental concepts and principles that we need in order to get started with this course. First of all, in order to work with the mechanics concepts, both statics and dynamics, we need to be able to measure things. Imagine that you have a rod in space. And so what does it have? Well, it has some kind of dimensions, right? It also has some kind of mass. And that rod is there for some kind of time. That means that we can also measure time. Let's say that this point here, that's center of mass. So the mass is equally distributed on this rod, and you have an equal amount of mass on this side and on this side. And then, if this center of mass here undergoes some kind of acceleration, then you must have an unbalanced force acting on it. And if this rod undergoes angular acceleration, meaning that it rotates faster and faster or slower and slower, then there must be an unbalanced moment acting on this rod. You will see that we'll be working a lot with forces that are measured in newtons and moments that are measured in Newton meters. However, they are not the fundamental quantities. The fundamental quantities are length, time, and mass. We measure length in meters, time in seconds, and mass in kilograms. These are the SI units for these quantities. And these are the fundamental quantities, which means that the units of other quantities, such as the units of forces, the Newton, and the units of moment, the Newton meter, they can be written in terms of these fundamental units right here. So let me give you a small exercise here. Just give it a thought before you watch the next video. How would you write the force unit, Newton, and the moment unit, Newton meter, in terms of these three fundamental units? How would you express Newton and Newton meter in terms of meters, seconds, and kilograms? Here's a little hint for you. In physics, you have something called linear momentum, and it's mass times velocity. Or in symbols, we can just write it down like this, m times v. The unit of mass is kilogram, and then the unit of velocity, that's meters per second. That's what velocity is, the change of position or length with respect to time. That's why it's meters per second. And so force is the change of linear momentum with respect to time. In other words, F equals the derivative of m times v with respect to time. So dmv with respect to dt. So it's a time derivative, the change of linear momentum with respect to time. And then if you take that force that points in a random direction, let's say here, and let's call its magnitude F, and then if you draw a perpendicular line to this force vector up until this point, and let's call it A, and this line is perpendicular to the force vector, and the length or distance of this line is d, then you have a moment about point A, and it equals F times d. And of course, this d has the unit of meters, and that's why moment has the unit of Newton meters. So Newton comes from here, and then meter, it comes from here. And so using these hints, how would you express the units of force, the Newton, and the units of moment, Newton meter, in terms of length, time, and mass only? Give it a shot and let's talk about it in the next video. Thank you very much.